In example 5, we're going to use Descartes' rule of sign to determine the possible number of positive and negative zeros. We saw that in the last video, when we're trying to look for the possible rational zeros, there can be quite a few options depending on what the numbers are for the constant term and the leading coefficient. And so if we can have a way to maybe minimize the number of possibilities, that helps us find zeros more quickly. So Descartes' rule of sign says that we can look at the sign changes between the different terms in the polynomial to determine possible positive and negative solutions. In the example A, I can see that there's a sign change here between the first and second term. The first term is positive and the second term is negative, so I only have one sign change. In this first line here, we have plugged in positive x to the function, so that means that there is either 1 or less than 1. In this case, it would only be 0 positive real roots. So when we were looking at those lists of all the pluses and minuses, if we found one that was positive, one of the zeros was positive, then we wouldn't need to test any more of the positive values because there could be at most one. What we'll do next is we'll plug negative x into the polynomial. Anytime that I have an even power, when I plug negative x in, I'm still going to get the same exact thing back. So in this case, I'm also still going to have one sign change. And that means that there is at most, either 1 or, in this case, 0 negative real roots. This is because when we have complex roots, roots that have imaginary numbers associated with them, they show up in conjugate pairs. So we always have to subtract off 2 at a time from the total number of roots that we have. In this case, we have 4 total. So let's look at the graph and see if this kind of matches up with what we're seeing from Descartes' rule of sign. So here's the graph that we were of the function we were just looking at, and it does show that we're seeing 1 0 that's negative, and we're seeing 1 0 that's positive. And so it looks like if we were to factor this, the other zeros are going to be imaginary numbers. And the reason I know that is because the graph is going through the x-axis. That means that each of those zeros, the positive and the negative, only show up one time. If the graph were sitting on the x-axis, that means that we have a multiplicity and that there might be 2 of those showing up. So this matches up with what we saw from Descartes' rule of sign. Let's look at another example that has more terms in it. We have positive x being plugged in, and we're looking at the number of sign changes between the terms. We have one here where we're switching from positive to negative. One here, we're switching from negative to positive, then here, positive to negative, and here. So it looks like we have at most 4 positive real roots. So there are either 4 or less than 4, subtracting off even integers, so 2 or 0 positive real roots. All right, and then what we'll do is we'll plug negative x into the original. Again, anything that has an even exponent will stay the same. Anything with an odd exponent will switch sign. And so when I plug negative x in, I don't have any sign changes. So that means that there are no negative real roots. If I were trying to use the rational zeros theorem, I would just not even check any of the negative values because none of them are going to show up. Let's look at the graph in Desmos to see if this matches up with what we're finding. So here's the graph of the function we were just looking at. And we do see that we're getting, in this case, we're getting 2 positive real roots, and we're getting 0 that are negative. So the original is raised to the 4th power. Since we're getting 2 positive real roots, that means that 2 of them are going to be imaginary roots.